So the upper endpoint of our 90% confidence interval is going to be our sample mean plus the margin of error. All right. Okay, but what's our margin of error? Well, our margin of error, we discovered on the PowerPoint, is equal to this critical z-value times the standard error of our sampling distribution, which is the standard deviation of our population divided by the square root of the sample size, lowercase n. Therefore, this 90% confidence interval is going to take on a more specific look here. And for the critical z-value, we got what? 1.645, correct? So we put that in for a critical z-value here, 1.65 times the standard deviation of our population divided by the square root of the sample size. That'll be the lower end point of our 90% confidence interval when you work this out. And again, you will be given or provided with the standard deviation of the population and also the sample size and the sample mean. The upper end point of this 90% confidence interval is going to be the sample mean plus our margin of error, which is 1.65 times the standard deviation of the population divided by the square root of the sample size. This is going to be a 90% confidence interval right here. Okay. Any questions how we build a 90% confidence interval manually? This is how we would do it. All right. Now, how would we build like a 95% confidence interval? 95% confidence interval. Well, build a 95% confidence interval. Well, we're going to basically go through the same routine. We just got to find the critical z values. So again, if this is a standard normal probability distribution, we want 95% of our sample means to be close or bunched up near or in the vicinity of our unknown population mean, mu. And we got to find these critical z values here. So to build a 95% confidence interval, the area of the standard normal distribution between these critical z values is going to be 95%, 0.95. So 0.95 is equal to 1 minus alpha, which implies that alpha is going to be equal to 0.05. And so, ladies and gentlemen, the area in the upper tail or lower tail of the standard normal distribution is going to be alpha divided by 2 here. And this lower tail area will also be alpha divided by 2. Well, what's 0.05 divided by 2? It's going to be 0.025. So that's going to be the area in the upper tail and the area in the lower tail. So to find our critical z values, plus or minus z sub alpha over 2, we're going to turn it over to our inverse norm function on our calculator again. The area below of which this lower endpoint critical z value is going to be 0.025. That's the area to the left of this. Mean of 0, standard deviation 1 for the standard normal distribution. Okay, get on your calculator and tell me what are going to be my critical z values for a 95% confidence interval. What are going to be these z values here for a 95% confidence interval? Just dial it up on the calculator, and hopefully you discover
that's negative 1.959.
Yeah. Okay, so negative 1.595959 was it or something? Something like that. All right, your author rounds it off to about negative 1.9. Wait a minute. This is not right. Wrong. Negative 1.959, I believe. Correct? Yeah, there you go. Sorry about that. Author rounds it off to about negative 1.96. And so those would be your critical z values for a 95% confidence interval, negative 1.96 and positive 1.96. All right. Those are your critical z values for a 95% confidence interval. And notice that these values, these critical z values, are further away from the mean of 0 here, okay? So when you increase your level of confidence, your z-values increase. All right, so therefore, our 95% confidence interval is going to be the sample mean minus 1.96 times the standard deviation of the population divided by the square root of the sample size to the sample mean plus 1.96 times the standard deviation of your population divided by the square root of the sample size. This is what a 95% confidence interval is going to look like. Anybody see that there? All right. Finally, for a 99% confidence interval, what would be our critical z-values? Well, now we want to be 99% certain that the majority of our sample means bunch up or congregate, if you will, around the population mean here. So our 99% confidence interval, which is going to be in here, requires that we, at 99% of the area of the entire standard normal distribution curve, lie in between our critical z-values here, and here. Well, 0.99 is equal to 1 minus alpha, which means alpha is equal to 0.01. So alpha divided by 2 is going to be 0.005. That's going to be the area allocated to the upper tail, 0.005. And alpha over 2 would be the area allocated to the lower tail of the standard normal distribution, 0.005. All right, and therefore, we got to get our critical z-values here. So we use our inverse norm function again. The area below our lower tail critical z-value is going to be 0.005. And the mean standard deviation is 0 and 1. Get on your calculator, dial that up, and tell me what your critical z-value is going to be now for this 99% confidence interval.
Negative 2.575.
Okay. Negative 2.575. Author rounds it up to about negative 2.58. And there you go. Negative 2.58 up to positive 2.58. 90% of your sample means will lie within this interval. Okay. And that leaves 1% of your sample means to lie equally allocated in the upper tail and the lower tail of the standard normal distribution. Okay. All right, so therefore, like, I'm going to build a 99% confidence interval. What's it going to look like? It's going to look like this. Your sample mean minus 2.58 times your standard deviation of your population divided by the square root of the sample size up to the sample mean plus 2.58. This is a 99% confidence interval. Okay. Now, of these three intervals, which one is the widest? Which one is the widest interval? Well, that'd be the interval that has the largest critical z-values, do you agree? Which is going to be the 99% confidence interval. This one is the widest interval. The one of these three that is the narrowest would be the one that has the smallest critical z-values. This one, the 90% confidence interval, is the narrowest. All right. Can anybody remember what I said last week as far as a little paradox or inevitable trade-off that we got going on here between the width of our confidence interval versus the level of confidence? Can anybody describe for us what I said last week? Does anybody remember what I said last week with regards to those two aspects, the width versus the level of confidence? Well, I'll say it again. Ladies and gentlemen, if you increase your level of confidence, and who would not want to do that, correct? Why would we mess around with a 90% confidence interval if we could be 99% sure that our unknown population mean mu lies in this interval? Why mess around with these lower confidence intervals here? Well, here's why. Because we have a little trade-off here, a little dilemma. If I increase my level of confidence, ladies and gentlemen, my confidence interval becomes wider. So yes, I am more certain, if you will, or more confident that my unknown population mean mu lies in this wider interval. But I'm less precise in determining its exact value because I have more values in this wider interval to choose from. So yes, I have a larger confidence, but I have a lower precision. Well, if I lower my level of confidence, now I'm not as confident that my unknown population mean mu even lies in this interval. But ladies and gentlemen, if it does, I have more precision in determining its actual value because this interval is more narrow. I have less values to choose from in this interval here. So it's a trade-off between confidence and precision. Increase your level of confidence. When you increase your level of confidence, your precision goes down. You decrease your level of confidence, your precision increases. You see that there? So I have a question for you. How do we have our cake and ice cream and eat them both? How can we enjoy both luxuries of having a high level of confidence and also a high level of precision? Anybody? What did I say? What did I stress last week? Does anybody remember how we can have both? How can we get both these together? Confidence and precision. High level of confidence and high level of precision. We would have to do what with our sample size? We would have to increase the size of our sample. And because, ladies and gentlemen, when we increase the size of our sample, this fraction gets smaller and smaller and approaches zero. So does this one. So does this one. So your margin of error gets smaller and smaller and approaches zero, which means our confidence interval gets narrower and narrower and narrower, increasing our level of precision, and yet we can still maintain a high level of confidence. You heard the old phrase, bigger is better, agree? Well, in statistics, when, ladies and gentlemen, building a confidence interval or conducting hypothesis testing, a bigger sample is always better. The larger sample you can choose from your population, the smaller your margin of error will be between your sample result and your unknown population result. Okay, so I have a question. Why don't we just poll everything in the population and not even have to deal with a margin of error? What's the problem with that, ladies and gentlemen? Why don't we just sample everything? Sample the whole population. Why mess around with this sample stuff? This margin of error. What's the problem with that in most situations?
Time and resources, you can't sample or you can't get everything from the whole population if it's bigger.
Yeah, populations in reality oftentimes number in the hundreds of thousands or millions and millions of data points out there in the real world, ladies and gentlemen, in which case we just don't have the time or the resources to, fathom or deal with such a large, size of numbers. For that reason, we're at the mercy of this concept of reaching into the parent population and pulling out a good, simple, random sample, and then having to go to bat for us. We use this powerful central limit theorem, okay, and the concept of a sampling distribution of sample means and probability theory go to bat for us in building these wonderful confidence intervals. Not only, ladies and gentlemen, are we corralling our population mean within these intervals, but we also have some measure as to how accurate we are in saying that the population mean belongs in one of these intervals. That level of accuracy is our level of confidence that we set. We are the ones that set the level of confidence in building these intervals. Granted, there's that inevitable trade-off between precision and the level of confidence. So you want to try to choose an appreciably large sample, as large as you can possibly, handle financially or whatever. The larger sample, yes, the better your results are going to be. But again, we have to deal with sampling because our population usually is just too large. Okay. Let's go back to the PowerPoint now. I did take this this little side street, or little side road here, ladies and gentlemen, to give you a more detailed idea as to how we're finding these critical Z values in building a confidence interval here. Okay, I want you to try this one. This is a classwork, ladies and gentlemen. You seen how I found the critical Z values for a 90%, 95%, and a 99% confidence interval. What if I wanted to build, are we ready for this? What if I wanted to build a 78% confidence interval? Classwork number one, I want you to get on your calculator and I want you to find for me what the critical Z values will be for a 78% confidence interval. You guys go ahead and do that. We'll call that classwork one. I want you to find plus and minus Z sub alpha over 2, the critical Z values, to build a 78% confidence interval. This is one that's not normally built, okay, but I want you to build it using your calculator to find those critical Z values. Go ahead and do that. You can round your critical Z values off to 2 decimal places, the hundredths place, please. Okay. Rounded off to 2 decimal places, are we getting positive or negative 1.23?
Yes.
All right, those would be critical Z values. So you're gonna have one down here, which is negative 1.23, and your upper endpoint critical Z value is gonna be positive 1.23. Those would be the critical Z values you'd have to use to build a 78% confidence interval. So it'd be X bar minus 1.23. That's your lower endpoint. Your upper endpoint of the interval would be this. All right, there you go. Okay, so there might be times when maybe your author, maybe Alex even wants you to build a weird confidence interval, one that's not your run-of-the-mill. Run-of-the-mill again either is 90%, 95%, or 99%. Those are their typical values. But sometimes they'll have you build one, maybe like build an 80% confidence interval or 78%. This one's really rare. Okay, but I'm showing you how to do it if you want to do that. Okay. All right, let's go back to the handout now. Okay, here's an example. A random sample of 36 people has seen a mean of 4.1 movies in the last year. Assume that the population standard deviation of movies seen per year is 1.7 movies. This is just an average. I mean, there's no such thing as seeing 1.7 movies, okay? But it's an average. All right, among these 36 people. What is the best point estimate for the mean number of movies seen per person per year by all people in the entire population? Because this 36 people just constitutes a small sample from the population, which might number in hundreds of thousands or millions. Okay. Well, the best point estimate for the mean number of movies seen by all of our millions of people in the population, let's say, would be the sample mean. The sample mean would be about 4 movies per year. But the problem with that, ladies and gentlemen, is we don't have any measure of accuracy as to how close or far away that 4.1 is to the actual unknown population mean number of movies that all of our people see in our population on average in a year. Because of that, we need to build a formal confidence interval to ascertain our level of accuracy here. So we're going to build a 90% confidence interval for the unknown population mean. Therefore, since it's a 90% confidence interval, we're going to use our critical Z values of positive and negative 1.65, which we discovered. Sample mean is 4.1, and our population standard deviation is known to be 1.7 movies. The sample size is 36. So if you get on your calculator, you'll be able to dial up the lower endpoint here of this 90% confidence interval as being 3.6. The upper endpoint of this 90% confidence interval will be 4.6. And there you go, ladies and gentlemen. There is our 90% confidence interval. And how would we interpret what this interval is telling us? We would say that with 90% certainty, okay, or we are 90% confident that the mean number of movies that all of the people in our entire population see on average in a given year is between 3.6 movies and 4.6 movies. That's a 90% confident, and we're 90% confident in saying that that's the case. Okay. And so there you go. That's a 90% confidence interval. Everybody understand how we just did that there? This is the manual way of building that 90% confidence interval. What would change? What would be the only thing that I would change if I went from a 90% confidence interval to a 95% confidence interval? What would I have to change in this formula? Anybody? If I up my level of confidence from 90 to 95%, there would be only one change. What number would have to change?
The Z value.
The critical Z value would go from being 1.65 to 1.96. You'd have to put 1.96 in here, and then crank out your new 95% confidence interval for the unknown population mean. Of course, that would be a wider interval, and the precision of knowing exactly what value mu would take on in that interval would decrease. although we would increase our level of confidence. Okay. Ladies and gentlemen, I'm going to show you how to build this interval now using our calculator. We have a wonderful function built in that will build this confidence interval very quickly for us, where we don't even have to tinker around with computing the margin of error, et cetera, et cetera. So why am I showing you the manual way of computing the margin of error? Well, ladies and gentlemen, because Alex might ask you a question. Alex might want you to just compute the margin of error, okay? And I'm showing you how to compute the margin of error. Or maybe Alex might ask you to find just the critical Z values for a particular level of confidence interval. I've shown you how to do that. So it's important to understand the ingredients that are going in to building these intervals here. But now let's take the express way. Let's bring up our calculator. And I'm going to show you the quick way for building confidence intervals for an unknown population mean mu when the population standard deviation is known. All right, bring your calculator up, hit the stat button, go over to tests. And now, ladies and gentlemen, we're going to scroll down till we run into the Z interval function, Z interval. They call these Z intervals because these confidence intervals we're building relies on the standard normal or the Z probability distribution. It's that distribution that are giving us our critical Z values in order to build our margin of errors to actually determine the endpoints of the confidence interval. I want you to bring up the Z interval function by hitting enter. Normally, we're given stats that are already provided for us from the sample. So select stats, not data. And now, as I'm, you got to go down and indicate what the population standard deviation for this problem was. And what was it? Well, they told us the population standard deviation was 1.7. So we type that in. Enter. The sample mean was 4.1. Enter. The sample size is 36. Enter. And now we set our level of confidence. This was a 90% confidence interval, so I'll type in 0.90. And we just calculated. It's that simple. So just populate the fields according to the information that is provided in the problem. Calculate. Here we go. Boom. Done. And there it is. Your 90% confidence interval is from 3.634 to 4.566. And that's it. We're 90% confident that our unknown population mean or average number of movies taken in by all of the people in our population, like I said, which could number in the millions, is between 3.634 movies and 4.566 movies on average per year. Okay, and we're 90% confident in saying that mu is actually in here, this interval. Make sense? Okay. All right, so that's how you build confidence intervals. What was the function again? Uh-oh, have we forgotten already? What was it called? To building these intervals. It was called the what function? Anybody remember? It was called the... What function is it? Do we remember?
Number 7 for Z interval.
Yep, the Z interval. Again, the Z interval constructs confidence intervals for an unknown population mean when the population standard deviation is known. It's always the Z interval. Okay. All right. Well, let's go to our textbook, Lingo, and have a little bit of fun before we will then entertain the last aspect of this section, which is a sample size problem. Wait a minute. Hold on a second. Did I don't think I even logged in. I thought I logged in here. Let's see. Let's see. Okay. Okay. Okay, let's go to our textbook. All right, these problems will be coming from section 7.2. All right, problem number 9 is the first one that I would like you to try. This will be classwork number 2. You can use your calculator and use the Z interval function to build your interval. So it should not take a long time. A random sample of 32 months has a mean of 52 automobiles stolen per month. The population standard deviation was 4 automobiles obtained from a long-term study. Find the 95% confidence interval for the mean. Okay, go ahead, call that classwork number 2. Find the 95% confidence interval for the mean number of automobiles that are stolen per month. Classwork 2. Use the Z interval function on the calculator. You do not have to do this problem manually. Okay, so it's pretty simple to build a confidence interval. All you gotta do is you bring your calculator out. Stat, go over to tests, go down and grab the Z interval function. Now, we select stats as opposed to data. Standard deviation time was what? 4. The sample mean was 54. Sample size was 32 months were surveyed randomly. 95% level of confidence, 0.95, and we're ready to calculate the interval. And there it is. And so we are 95% confident that the average number of automobiles stolen per month, okay, for the entire population, which is going to be for many months, many years, on average would be about 52.6 vehicles to 55.4 vehicles per month are stolen. And we're 95% confident in saying that the population mean number of vehicles stolen per month lies in this interval. Okay. Everybody get that there? Any questions on that? That's how you build a Z interval or confidence interval for an unknown population mean. All right. What if we're given raw data? For instance, problem number 14 here. Let me double check number 13. Let me see what's going on here. Okay. What if we were given a raw data set here and we wanted to build a confidence interval here? Okay. Well, what you can do is you can use your calculator and you can literally put the raw data into a list. Let's see if I can do this here. So you can put all this data into a list here. So stat, edit, and in list one, you can type in all this data. So 1.9, 2.8, 2.5, 3.1, 2.0. Two point 1, 3.2, 3, 2.7, 2.7, 2.8, 2.4, 2, 3.8, 2.8, 3.5, 1.9, 3, 2.9, 2.7, 3.2, 3.8, 4, 3.4, 2.7, 2, 3, 3.9, 2.2, 2.9, 3.3, 1.9, 3.8, 2.7, 2.8, and 2.1. All right. So now we can build a confidence interval here. I guess they want a 99% confidence interval here. Suppose they did not give you the population standard deviation, then you'd have to use a sample standard deviation as a point estimate. But we would have to conduct a T interval, build a T interval, not a Z interval. We're not into that today. So as I've noticed, they did indicate that the population standard deviation is to be assumed to be 0.62. Let's get out of this now. Second mode to quit. Let's go to stat, tests, select the Z interval, function number 7. Notice now you have to be on data because we're using raw data. The standard deviation of our population, again, is assumed to be 0.62. Our raw data has been put into list 1, and the frequency, just leave it as 1. The level of confidence is 0.99. And calculate. And there you go. That would be your 99% confidence interval for the unknown population mean, mu, 2.55 to about 3.09. So we're 99% confident that our population mean lies in this interval here. Okay. So that's how you would deal with it when you have a raw data set. Alrighty. Any questions about that there? Raw data set.
Can you go back over what you put in the calculator after you highlighted data?
Well, I first of all, I typed all my data in. You see that first? I put
Yes.
all the data in list 1. So then we're good on that. Then you just go back to stat, tests, and then you got to go down and get the Z interval function, number 7. Hit enter. And then you want to select data. because we have a raw data set here. We don't have the, the sample statistics handed to us, like the sample mean, okay, X bar. Now, we could have found X bar using one bar of stats, our function one bar of stats to find X bar, and then we could have just used, to build a confidence interval selecting the stats feature. But I want to show you how, when given a raw data set, how you do these confidence intervals. So we select data and type in the population standard deviation, which they told us in the problem was 0.62. List one, you got to have the name of the list that contains your data, and my list is list one. Frequency level is 1. That means every data point has an equal weight of 1. Level of confidence is 0.99, a 99% confidence interval, and just calculate. That's it. Just hit enter, and that would be your interval. Okay, that is your 99% confidence interval for the population mean. All right. So that's that there, ladies and gentlemen. Got that there. Okay. So let's see here. All right, so you guys go down and do this one using your calculator. Just when I got down demonstrating for you, I want you to type this data in list one here for number 15. And I want you to build a 98% confidence interval for the unknown population mean mu. Assuming the population standard deviation is 3. Go ahead and do number 15. We'll call that classwork number 3.
I have a question. Mhm.
Okay, go ahead.
Could you scroll back up to classwork number 2? I want to write down the problem.
Number 2, okay, hold on a second. Number 2 was problem number 9. Okay, the automobile problem. You see that?
Oh, okay, that was
95% confidence interval. Okay,
okay. Thank you.
that was number 2. All right, let's go down to number 15 again. Go ahead and do that one, classwork 3. Okay, so what would be the 98% confidence interval for the mean number of discipline problems that occur each month at a large high school? And the confidence interval should be from 18.7 up to 21.2. Did anybody get that there? After typing that data in, using a standard deviation of 3 for the population. Anybody get that?
Yep.
Okay. All right, now I want to go back to number 12. And again, you can use your calculator. And let's see. All right, number 12 will be classwork number 4. I would like you to do A through D there. Now it looks like it's going to take a ton of time, which is not the case at all. Ladies and gentlemen, it's not a raw data set. All you got to do is just use your Z interval and crank out a 95%, 99% confidence interval. That's not going to take too much time there. Go ahead and do that and maybe answer questions A and D also. All right, we'll call that classwork number 4. Okay, so a best point estimate for the unknown population mean would be the sample mean, which would be 7.2. But the problem with that is that we don't have any measure as to how accurate that is. Could be pretty close, could be very close to the unknown population mean, but it could also be very far away. We don't know. That's why we build in confidence intervals, right? So 95% confidence interval, I got those endpoints, and for the 99% confidence interval, I got that point, those endpoints. And which interval is narrower? In other words, smaller. That would be the 99% confidence interval. Do you agree is more narrow compared to the 99% confidence interval? And the reason why is because the 95% confidence interval has a smaller critical Z value. So its margin of error is smaller than a 99% confidence interval. All right, did anybody get those values at all? Any of the?
Yep.
All right, so ladies and gentlemen, do we know how to build confidence intervals in our calculator, both manually and using our Z interval function? All right. Now we're going to wrap up today's lecture by looking at the last aspect of this section, and that's called a sample size problem. Picking a sample size is a trade-off. We found out that a larger sample size is harder and more expensive to find and to study. On the other hand, a large sample size makes confidence intervals more accurate. Recall that the margin of error of our confidence interval is E, which is given by the product of the critical Z value and the standard error of the sampling distribution, which is the population standard deviation divided by the square root of the sample size. As the sample size increases, the margin of error decreases because the denominator gets larger and larger and larger, forcing the fractional value to approach zero. However, there are diminishing returns. In order to cut the margin of error in half, we would have to quadruple our sample size. Now, you may or may not be in a position to, do so. And if you're not in a position to do so, that is a huge problem. Okay. In order to pick an appropriate sample size, or determine the size of sample we should choose from the parent population, we should first of all decide on how large of a margin of error we're willing to tolerate. All right. And once we know the margin of error that we're willing to tolerate, we can then use what's called our sample size formula to determine our sample size. All right. Now let me show you where that formula came from here. I'm going to derive it for us. We know that for these confidence intervals, the lower endpoint is a sample mean minus our margin of error. And the upper endpoint is the sample mean plus the margin of error. Okay. The margin of error, E, determines the width of our sample, our confidence interval. All right. How would we, ladies and gentlemen, how would we determine what size sample we would need? Well, our margin of error, or MOE value, sometimes it's called margin of error, MOE, is this formula here. I'm just going to use E because it's simpler to work with than MOE. It just looks more compact. All right, we found out that it's our critical Z value, depending upon our level of confidence, times the standard error of the sampling distribution, which is to say the quotient of the population standard deviation and the square root of the sample size. I'm going to solve this equation for the variable n, the sample size, by employing algebra on this equation. How do I get n by itself? First of all, let's divide both sides of our equation by the critical Z value to knock this thing out. So we got to divide the left side by the critical Z value. And when we divide the right side by the critical Z value, it's going to disappear. So this reduces out to 1. Therefore, it leaves us with E over our critical Z value equal to the standard deviation of the population divided by the square root of the sample size. remember, we're trying to solve for the sample size. What I could do is reciprocate both sides of this equation and still have an equivalent situation. So I will flip both sides upside down. And now I have my sample size at least, albeit underneath the square root in the numerator. Now, ladies, I'm going to multiply both sides by the standard deviation to get rid of this fraction on the right side of my equation. And when I multiply the right side by the standard deviation, what happens to it? It cross cancels out, leaving us with the square root of n. Now, how do we get rid of a square root? Anybody? How do we get rid of a square root? We raise a square root to what power to get rid of it?
Second power.
You square it. That's right. So we're going to square both sides of our equation. And when you square the left side and square the right side will just have n. So we have derived what's called the sample size formula that will give us the size sample we should choose from a population to ensure that our sample mean does not stray any more than E units away from our unknown population mean, okay, with a certain level of confidence. All right. This is called your sample size formula, ladies and gentlemen. Unfortunately, our calculator cannot do a sample size problem directly, so this is a formula you're going to need to know when you take it to Alex. This is called your sample size formula, so make sure you have that handy or memorized. Again, E is the allowable margin of error. Z is our critical Z value depending upon our level of confidence. This is your standard deviation of your population of which we assumed today that we know it. That's your sample size formula. Okay, let's go show ourselves how this sample size formula can help us do some problems now. This derivation, you are not responsible for it, but I just thought I would show you quickly where it comes from so we can appreciate from whence it came. Okay. Okay, ladies and gentlemen, let's go employ this formula called a sample size formula and show ourselves like what kind of a problem it could be used for. Okay. Whoops, let's see here. All right, now let's see. Okay. Earlier, we constructed a 90% constant interval for the mean number of movies seen per year, where the population standard deviation was assumed to be 1.7, and our critical Z value for a 90% constant interval is like 1.645, which we call it 1.65. Of course, that's found by the inverse norm function. And we got a margin of error of 0.5 with a sample size of 36. Suppose, ladies and gentlemen, we wanted to lower our margin of error. Suppose we wanted our error between our sample mean and our unknown population mean to be no larger than 0.25. In other words, we do not want our sample mean straying any further away from our unknown population mean than 0.25 units. And suppose that we want to be 90% confident that this is the case. So the question is, what size sample would we have to extract from our parent population to ensure that our sample mean will not stray more than 0.25 units away from our population mean? And we want to be 90% confident that that would be the case. Well, we put things into the sample size formula. In for the critical Z value was 1.65, which is based on the fact that we want to be 90% confident. Our sample standard, population standard deviation is 1.7, and we don't want our margin of error to stray further than 0.25 units away, or to be more than 2.25 units for the difference between our sample mean and our unknown population mean. If you get on your calculator, dial this up, square the result, you get 125.6. But since I said with sample size, bigger is better, you want to always round up, never round down when it comes to sample size, always round up. So we'll round this up to about 126. Therefore, ladies and gentlemen, if I reach into this parent population and pull out a simple random sample of size 126 or larger, I would be 90% confident that the difference between my sample mean and my unknown population mean would not be any greater than 0.25 units. Everybody understand what we just accomplished there? It's called a sample size problem. All right. And sample size problems are conducted all the time before polls are taking, on a lot of your media outlets. They conduct a poll, and sometimes you'll see like a little plus or minus, percentage points. You ever see that? Plus or minus? Okay. Well, that's the allowable margin of error, ladies and gentlemen. And that determines what size sample they're going to have to choose from the parent population to be a certain level percent confident that your sample result will not stray any further away from the unknown population result than that allowable margin of error there. Okay. All right. So let's go see in our book where one of these problems would hang out. Called a sample size problem. All right, it looks like I got timed out or something here. So. All right, the sample size problems. Where do they hang out? Okay. All right, problem 23. I will go down and look at this problem here. I will work this one out for us. And then I'll have you do one for classwork here. Number 23, it says, a researcher wishes to estimate the average number of minutes per day a person spends on the internet. How large a sample must she select if she wishes to be 90% confident that the population mean is within 10 minutes of the sample mean? Assume the population standard deviation is 42 minutes. Okay, so ladies and gentlemen, this is a classic sample size problem, and I'm going to demonstrate to you how to go about this problem, and then I'll have you try one. Okay, so what do we know? Well, first of all, to the party, you have to import the sample size formula. You're going to need that. And without going through the derivation again, here is the sample size formula that we are going to use. E again is the allowable margin of error. Between our sample mean and the population, the unknown population mean. This is our critical Z value based on 1 minus alpha level of confidence. And of course, this is the what? The known population standard deviation. Today, we're assuming that we know the population standard deviation. We will show you what happens when we don't know the population standard deviation, which usually is the norm, by the way. We'll still be able to build these confidence intervals, but we have to use a different probability distribution to do so. All right, so here we are, ladies and gentlemen. Now, in this formula, what do we know from our word problem? What do we know? Let's go back and investigate. I forgot it already. Number 23. How large a sample must she select if she wishes to be 90% confident? Okay, right there. If we want our level of confidence, ladies and gentlemen, to be 90%, what's our critical Z value is going to be? Does anybody remember? 90%?
1.65.
Yes. So our critical Z values are going to be positive, negative 1.65. That's your critical Z value. Now, it don't matter whether you put a positive or a negative 1.65 in here, because what are we doing with this? We are squaring the result. Because you're squaring it, it don't matter if this is positive or negative in here. When you square it, it will always be positive. Okay, so sample size is never going to be negative. It's always going to be positive. All right, yeah, we'll use 1.65. What else do we know that they gave us in this problem? Well, we want to be 90% confident that the population mean is within 10 minutes of the sample mean. 10 minutes. So what is my allowable 10 minutes? What would that be? For what quantity would it be here? The 10 minutes.
E.
Yeah, that's my allowable margin of error. That's as large as I want it to be. I don't want it to be any larger than 10 minutes for a difference between my sample mean and my unknown population mean. Okay. So yeah, my allowable margin of error is going to be 10. So E will be 10. Actually, 10 minutes. What else do we need? We got our critical Z value. We got E. We got to find our what? Our population standard deviation. And did they provide that for us? Yes, they did. They indicated that it was 42 minutes, excuse me. So therefore, we know our population standard deviation is 42 minutes. All right, let's take these values and plug them in or substitute them into the sample size formula. And for Z goes 1.65 times my standard deviation, which is 42 minutes. Divided by my allowable margin of error that I set. I'm the one that indicates I want it to be no larger than 10 minutes. And then I want to square this. Hey, what happens to the minute units here? The minute units drop out, as they should, because a sample size is a dimensionless number. So the minute units drop, and we just got to get on our calculator and dial this up. So let's get on our machine, make sure that you can do this. Make sure that you can do this on your calculator, and let's see what our sample size should be. So 1.65 42 divided by 10, and then I'm going to square that quantity. Remember, ladies and gentlemen, when in doubt, always round sample sizes up, never round them down. I'm going to bump this up to 49. There we go. 49. So, can anybody in plain English, plain words, explain to us what that 49 represents? What does that really mean? What did we just get done finding? What is that 49? Is that 49 minutes?
Then we need 49 people.
All right. So we need to sample. In fact, this is so important. I am literally going to burn some class time to write this down. That's how important it is. We would have to sample at least, okay, at least, what does this problem even pertain to again? I forgot. Hold on a second. Oh yeah, watching the internet. Okay, here. We would have to sample at least 49 people. to be what? 90% confident that our sample mean X bar, that our sample mean X bar, okay, is within 10 minutes of our population mean. And the population mean is mu, okay? So as long as we select a sample of size 49 or larger, we can be 95% certain or 95% confident that when we compute the mean of that sample, ladies and gentlemen, that sample mean will be in no more error when compared to the population mean, or the unknown population mean, than 10 minutes. In other words, the difference between the population mean and the sample mean will be no larger than 10 minutes. And we can be 90% confident in saying that when we select a sample of at least size 49 from this population. That's what that 49 is saying. This is a classic sample size problem here, okay? Now, we know what size sample we should choose from our parent population to ensure that our sample mean is within 10 minutes of our actual unknown population mean. So we have a very, very good idea as to the amount of accuracy, okay, we have going on for us here in using our sample mean of a sample size 49 or larger to estimate or guesstimate the unknown population mean. All right. So that's a classic sample size problem. Now, I have a question for you, Liz. Why doink around with a 90% confidence level when we could bump it all the way up to 99%? What would that do? What happens? What would happen if you increase the size of your level of confidence? What happens to the Z's, the critical Z values? Does it increase or decrease if I went from 90% up to 99%? What would happen to the Z value here?
Increase.
That would increase. And since that would increase, that means our sample size would what? Increase. But it would not increase linearly. It would increase what? Quadratically. Do you agree? Because this is a second degree power out here. So yeah, I mean, our sample size is going to increase big time when you just increase your level of your critical Z value or your level of confidence. So there's that inevitable little problem we fathom again. You increase your level of confidence, yes, that's a good thing, but that means you're going to have to choose a larger size sample. And you may not be in a position to do so, okay? Because you may not have the time or the resources to do so. So again, ladies, we got this trade-off here, this vicious trade-off between level of confidence and precision, okay? And that's the consequence of something called sampling error, and that we're having to sample. Now, if we just choose the whole population or poll the whole population, we don't have to mess around with any of this. We'll be 100% certain as to what the population mean is. Do you agree? But the thing is can you do it? I mean, these populations are in the millions of data points at times. All right, so that is a classic sample size problem. Now I want you to work out number 24, which is in your textbook. We'll call this classwork number, I forgot. Where are we? Up to 5 now or something?
Yeah, 5.
All right, number 24, cost of pizzas. That's a classic sample size problem. So go ahead and do that one. It's done the same way as I just did the last one. Number 24. Okay, so there we go. We want to use a level of confidence of 95% in computing the sample size. Therefore, our critical Z value will be 1.96. Our standard deviation is known to be 26 cents. Our allowable margin of error between the average cost of a cheese pizza from our sample and the unknown average cost of all cheese pizzas, okay, of our population to be no more than 15 cents. Substituting things into our sample size formula here and cranking out the result on the calculator, always round up again. We see that our sample size would have to be at least size 12. And therefore, we would conclude that we would need to select a sample of at least size 12 to be 95% confident that the difference between the sample mean cost and the unknown population mean cost of I guess it's a cheese pizza, would be no more than 15 cents. Okay, so our sample mean will be within 15 cents of the actual unknown mean cost of all cheese pizzas in our population, which could be number in the millions. Okay, would be no more than like 15 cents there. Right? Classic sample size problem. Did anybody get that?
Yep.
Okay. Let's see. Okay. Number 25, we could have you work on this last one here. We'll call this the last class work. If the variance of the water temperature in a lake is 28 degrees, how many days should the researcher select to measure the temperature to estimate the true mean lake temperature within 3 degrees with the 99% level of confidence? Warning here, ladies and gentlemen. What do they give you here? They don't give you the standard deviation. They give you the what? The variance, correct? This is not a standard deviation. It's a variance. So what are you going to have to do to this since you need a standard deviation? You're going to have to take the what? Since that's the variance. Remember, standard deviation is equal to the square root of the variance. So you got to take the square root of 28 degrees first to get the standard deviation, and then you go from there. All righty, go ahead. We'll call it the last class work, number 25. Okay, so we want to build a 99% sample size problem here, so our critical Z value would be 2.58. Standard deviation is the square root of the variance of 28, which is about 5.29. Allowable margin of error between the sample mean and unknown population mean temperature of the lake is 3 degrees. Put things in, crank it out, and therefore we get about a sample size of at least 21. And as a result, to interpret what this is saying, we would, ladies and gentlemen, have to sample at least 21 days or more in order to be 99% confident that our sample mean temperature, water temperature, will be within 3 degrees of the actual unknown mean water temperature of the lake for probably the whole year, okay, or for many, 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 many days. All right. And so that would be the result there. Did anybody get that?
Yep.
All right, so what we accomplished today is we learned how to build confidence intervals for an unknown population mean where the population standard deviation is known. And shortly in the near future, we'll be looking at how to do such a thing when our population standard deviation is unknown, okay, which is usually the case. We also looked at how to compute or estimate a sample size that would be necessary to be a certain, percent confident that our sample result will stray no more than E units away from our unknown population result, called a sample size problem. And we basically used this formula that was derived from the margin of error that is used to build confidence intervals. Okay. All right. So that's that, ladies and gentlemen. Oh, let's see here. That wraps it up for today. I'll stay on the line if anybody has any questions or comments. I'll field those. If not, have a good day, and I'll make sure that Alex is up to date with the homework. All right, take care.